So hello everybody. Probably all of you know me. I'm Nicolae Tsarfulea, a professor of mathematics, and today I'll be substituting for Dr. Norma Elias. Norma is a good friend of mine. She couldn't make it today, and she asked me to cover her classes, and I'm gonna do just that. You all know how handsome I am, and I don't want that to be a distraction. So I'm going to turn off the camera, and then we'll talk about mathematical induction. All right. I'll have to share with you my screen. Okay, so let's see this one. And let's talk about mathematical induction. By the way, you can ask me, you can stop me and ask me questions anytime you want. If you don't hear me or something happens with your image, the screen, let me know. Okay, so today we'll talk about a very powerful technique, which is, like I said, mathematical induction. So I'm going to write here. I hope you can see this. Let me know if you don't. So this is about mathematical induction. Okay, or for short, let me see, my handwriting is not the best here, or for short, just induction. Induction. Okay, or just induction for short. Okay, all right. So let's start by making a little conjecture. So in order to motivate the discussion, so let's start with little, this conjecture. We can observe a pattern and we can say, okay, if I add these first n even natural numbers, so 2 plus 4 plus 6 plus 2n, so the sum of the first n natural numbers, I make this conjecture that this sum is in fact n times n plus 1. Okay, let's do a table, see if this conjecture holds or not. So a little table. Don't expect my handwriting to be very good by using this tablet. So let me know if you have any problem with this. Okay, so let's say here I'm gonna say this is Sn, S sub n, the sum of the first n even numbers, even not natural numbers, and what I want to prove that this is n times n plus 1. Okay, so how do I do that? Well, of course, let's see, I take n equals 1. Then S1 means just 2 times 1, right? I mean, that's it. And obviously this equals matches our formula. This is 1 times 1 plus 1, obviously, right? So this is true. So this is true. This is true. Then if I make n equals 2, then S2 is what? Well, the first two natural, even natural numbers. What's this? Well, this is 6, right? But you also see that that's 6 is what? Is 2 times 2 plus 1. So that formula is verified again. And so on, right? I can verify this formula for many such numbers. So our conjecture is that if we sum all these n numbers, even numbers, the first n even numbers, we get n times n plus 1. Okay? All right. Well, are all of these statements true? I mean, we know the first one because it's very easy to verify, but is this one true? And mathematical induction is designed to answer just this kind of question, okay? Where here we have an infinite list of statements, like here, like in this example, S1, S2, S3, and so on, Sn, and so on, that we want to prove true. And the method is relatively simple. Okay, we can even visualize this by using this very simple domino example. So I'm going to show you that immediately. Do you see this, these dominoes? Do you see these dominoes? So
yes.
I mean, I want to exemplify this simple idea behind mathematical induction. Can anyone confirm, that the image is on your screen?
Yep, we can see it.
All right. Okay. So the first thing you have to prove, you have to prove that S1 is true. Okay. So the statements are lined up like these dominoes. You can see this is S1, S2, S3, S4, S5, and so on, right? To us, S1 was 2 equals 1 times 2. S2 was 2 plus 4 equals 2 times 2 plus 1. S3 would be 2 plus 4 plus 6 equals 3 times 3 plus 1, and so on and so forth, right? And if we prove that the first statement is true, right? Then after that, if we prove that that first statement implies that the second statement becomes true, and so on and so forth, like here. So if we suppose that the k falling domino always causes the k plus 1 to fall, we conclude that all dominoes must fall. So all these statements are true. That's the very simple idea behind the mathematical induction. Okay? So do you understand, this simple argument? Okay, so we assume that the first statement S1 symbolizes the first domino, S1, being knocked down. Okay, this will knock down the second domino and the third domino, and so on and so forth. And the conclusion is that all these dominoes are knocked down. Is this easy to understand? Okay, then let's see, the steps of this mathematical induction. So here I have to write it here. So this is the idea behind the proof by induction. So the proof by induction. The first step, the so-called the basis step, or step 1, right, is to prove that the first statement S1 is true. So prove that S1 is true. Like we did here, right? These statements can be anything. It's not about the problem above. I mean, our conjecture above. It's about any statement that can be indexed by natural numbers. Okay, that was the basis step. That is the basis step. Then, in order to finish this proof, you need to verify the second step, which is the so-called inductive step. Which is also, let's say, step 2, right? So the inductive step. And in this one, you need to prove that given k greater than or equal to 1, positive integer, obviously, right? Positive integer, natural number. Here we need to prove that the statement S sub k implies S sub k plus 1 is true. Okay, if we are able to prove these two steps, steps 1 and step 2, we can conclude. So if we can prove these two steps, then the statement Sn, S sub n, is true for all n. It's a very nice technique. It's a very powerful technique for proving all kinds of statements. And let me show you how to use this for our example above. I mean, for our conjecture, and then for many other examples. Okay, you can ask me questions anytime, like I said. Okay, you can stop me and ask me questions. So let's prove our conjecture. So let's prove our conjecture, proof of our conjecture above, right? So our conjecture was that 2 plus 4, maybe I should label this. This is our statement. So S sub k, this is our conjecture, is two plus 4 plus 2k equals k times k plus 1. This is what we want to prove, right? The base step, the basis step, the first step, right? The basis step. Well, it's obvious, right? So S1 means we have to prove that 2 equals, okay, k in this case is 1, right? So 2 times 1, I can say here. Just to be, rigorous. Equals k, which is 1, multiplied by 1 plus 1. Well, this is absolutely trivial. Okay, anybody can see that. So the basis step is satisfied. Now, the next step in the proof is to prove the inductive step. Okay, so here we assume Sk true, and we want to prove that this implies Sk plus 1 true, is true. This is what we want to prove, right? So this is our question here. This is what we want to demonstrate, okay? Well, Sk being true means that Q plus, so this is Sk. This is the statement Sk. Q plus 4 plus Q K equals K times K plus 1. Okay, then how do we prove? So here, if we add, if we add to the both sides, Q times K plus 1, right? To this equation, we add 2 times K plus 1 to both sides. Look what we get. We get 2 plus 4 plus 2K plus 2 times K plus 1 equals K times K plus 1 plus Q times K plus 1. Okay, this equals the right-hand side. I can factor out K plus 1. So here is K plus 1. And what's left is K plus 2. But this is exactly statement Sk plus 1. So this is exactly, so we just proved that 2 plus 4 plus 2K plus 2 K plus 1 times K plus 1 here equals K plus 1 times K plus 2, which is exactly our statement S sub K plus 1. So in other words, we are done with the inductive step. We are done because we proved that S sub K implies S sub K plus 1. So we assume that S sub K is true, and this implied S K plus 1 true as well. That's it. We are done. So from these two steps, 1 and 2, the mathematical induction tells us that, you know, Sn is true for all natural numbers n. Let's say greater than integers, right? Okay? Questions about this? This is just a very simple example of application. Again, mathematical induction is a very, very powerful technique. And let's see, you know, some other applications. Some of them are, you know, quite unexpected. For example, let's see another example here. Example 2, let's call it example 2. Let's prove that if n is a natural number, so is a natural number, you know, a positive integer, then 5 divides n to the 5th minus n. This expression. So this is our conjecture. Let's prove it. Okay. So again, we use, so here is the proof. we use mathematical induction again, right? So the first step, the basis step. The basis step. That's kind of trivial to verify. If we take n equals 1, so n for n equals 1, then obviously we have 5 divides 1 to the 5th minus n, minus 1, right? This is just 0. And obviously, you know, 5 divides 0. 0 divided by 5 is 0 again, right? So our S1, so let's say, no, this is our statement here. We call this statement S sub n. And so S1 is verified. So the basis step is verified. So for n equals 1, 5 divides 0. Now, the inductive step, so for the inductive step, what we do, we assume that Sk, I should have, stuck with K, or stick with, I should have stick with K, not N. N is, the general statement. Okay, so we assume that Sk is true. Meaning 5 divides K to the 5th minus K. And from here, we want to prove that, so this is our task, to prove that Sk plus 1 is true. Okay, this is what we want. Okay, so what does the statement Sk plus 1 says? So Sk plus 1 says that 5 divides K plus 1 to the 5th okay, minus K plus 1. This is what we want to prove. All right? How do we prove that? So this is what we want. Knowing that Sk is true. Well, let's expand this. Here you have a parenthesis, another set of parentheses. Okay, so let's expand this expression to on the right. So we have K plus 1 to the 5th minus K plus 1. Okay, so this is what? You probably remember the binomial expansion, Newton's expansion. So this is K to the 5th plus 5, choose 1. This is from combinatorics. I'm gonna give you a little bit more information after this about this notation. Times K to the 4 plus 5, choose 2 times K cubed plus 5, choose 3 times K squared plus 5, choose 1 times K plus 1 to the 4th, which is still to the 5th, which is still 1, minus K minus 1 coming from this part. Okay, all right, then let's see what we have. So this equals K to the 5th, okay, plus 5, choose 1 is 5. You have so you from a group of n objects, you have to figure out all possible choices of just one object. Well, it's 5, right? So this is k to the 4. Now, okay, so what's 5 choose 2? Let me give you the formula for these combinations. So in general, n choose k. This is the common notation. It's n factorial over k factorial multiplied by n minus k factorial. Have you seen this before?
Yes.
Well,
Saying yes.
okay. Well, in Europe, they denote it by this, C and sub k. This is the same notation. There are books which use this notation, in fact. Okay. Now, in our case, we all know what n factorial is and so on and so forth. So, for example, 5 choose 2. Oh, this is what I intend to say. 5 choose 2, not 5 over 2. This equals, according to that formula, it's 5 factorial divided by 2 factorial times 5 minus 2 factorial, right? 5 minus 2 factorial. Okay, so this is 5 factorial divided by 2 factorial times 3 factorial. What's this? What do you think you get at the end of this calculation? So what's 5 factorial? You actually can simplify. You can simplify by this. I mean by 3 factorial, which is 6, right? But you are left here with 4 times 5. And then, simplify by 2, you get 10. So I can say here this is 10 times k cubed plus, well, there is a nice property that says something like this here it's trivial. I mean, it's trivial to figure out this 5 choose 3. But in general, you have this equality. N choose k. It's always equal. Maybe I should be more careful with this handwriting. It's always equal to n choose n minus k. Just look at the formula for the proof. So 5 choose 2 equals 5 choose 3. So this is 10 again. K squared, can compute it directly, no problem. And then 5 choose 1, 5 choose actually 4 here, which is equal to 5 choose 1. So you have 5 again times k plus 1. Well, actually plus 1 minus 1, right? So plus 1 minus 1. Should I write it or just say, it's just minus k there? So here it's 5k plus, okay, minus k. I just, let me write it. It's plus 1 minus k minus 1, and this equals, so I'm going to move this calculation down here. So here is what I have. This equals k to the 5th. Now I can rearrange the terms of this of the right-hand side of this equation. So I can say here k to the 5th minus k. That's fine, right? And then whatever is left. So I have plus 5 k to the 4 plus 10 k cubed plus 10 times k squared plus 5k, and that's it, right? Now, keep in mind that we assume that k to the 5th minus k, which is this statement s sub k, is true, meaning that k to the 5th minus k is a multiple of 5. So I can write it in this form, equals 5 times 8. And so what I have here, I have 5 times 8 plus all the other terms, which I'm not going to write, And now I can factor out 5, obviously. If I factor out 5, I get a plus k to the 4 plus 2k cubed plus 2k squared plus k. Obviously, this is a multiple of 5. So we conclude. So this is a multiple. This is a multiple of 5. Obviously, you know. Then the conclusion is that S sub k plus 1 is true. I mean, 5 divides k plus 1 to the 5th minus k plus 1 is true. And this ends the proof because both steps are verified, right? So from 1 and 2, we have, you know, the conclusion is true. S sub n is true for all n. Okay? Questions about this? Let's do another one, which is similar to this, a bit similar. There are literally infinitely many such applications and exercises. Another one. Another example. Probably this is example 3. Okay, so I'm gonna say here that let's prove that this number 133 divides 11 to the n plus 2 plus 12 to the 2n plus 1. Okay, for let me see, I can say for n greater than or equal 0, right? The index doesn't have to start at 1. Can start at 0 as well. Can start at even at a negative integer, but the induction doesn't work for n over the entire set of integer numbers, because you cannot go to the left to infinity pretty much. You go only to the right. Okay, so here in this case, so here is the proof by induction. By induction, right? Mathematical induction. Okay, this is our statement S naught, right? This is the basis step. So this is our first step, step 1. So maybe I should say that, right? So step 1, basis step. Well, we want to prove, you know, that the statement S naught is true. That's not very complicated because obviously 133 divides 11 to the 0 plus 2 plus 12 to the 2 times 0 plus 1, which is what? I mean, this is what? It's 11 squared, which is 121, plus 12. It's exactly 133. So obviously, you know, the basis step is verified. Now, step 2, the inductive step. So here we assume Sk which says that 133 divides 11 to the k plus 2 plus 12 to the 2 times k plus 1, and assume that this is true. And what we want to prove, so this is our goal, is to prove that s sub k plus 1, this statement saying that 133 divides 11 to the k plus 1 plus 2 plus 12 to the 2 times k plus 1 plus 1 is also true. This is our, task. This is what we should do, right? Okay, how do we prove that? Well, look at the right-hand side. Look at this expression. So we can write 11 to the k plus 1 plus 2 plus 12 to the 2 times k plus 1 plus 1 under this form. I can write it as, okay, I say here 11 to the k plus 2 multiplied by 11. I haven't changed anything, right? Because this is 11 to the k plus 1 plus 1. It's exactly what we have in the first term on the left-hand side. It's k plus 1 plus 2, right? Plus, now 12. I can write here 2k plus 1. Why I do this is very apparent, because I want what I have, here, right? What I have in this step sk, which I assume true, okay? Multiplied by 12, well, the power here is 2. All right. So this equals 11 to the k plus 2 times 11, no problem here, plus here 12 to the 2k plus 1. Now 12 squared is 144, which is also 133 plus 11, no problem, right? I mean, so 12 squared is 144. I can split it as 133 plus 11. Makes sense, right? Okay, so what do I have then? I have 11 to the k plus 2 multiplied by 11 plus 133. I flipped the order of this product times 12 to the 2k plus 1 plus 11 times 12 to the 2k plus 1. Okay, I'm going to group these terms in a more suitable, more advantageous way. So I'm going to group this one and factor out 11. So here is 11 multiplied by 11 to the k plus 2. Okay, plus 12 to the 2k plus 1 plus all this plus 133 multiplied by 12 to the 2k plus 1. And now we can conclude, because you see this one here, SK says that this is a multiple of 133. So you can say this is 133 times the natural number 8, whatever that number might be. And this is also a multiple of 133. So you can factor out 133. And you end up with 11 times, this number A, whatever that number is. We don't care about that. It's about divisibility, nothing else here. And here you have 2k plus 1. But obviously, this is a multiple, which is, obviously a multiple of 100. So this is a multiple of 133, and we are done. So we just proved that sk plus 1 is true. So we assume sk true, and we prove that sk plus 1 is true. Okay, how cool is that? I mean, this is really interesting, right? So done. So, you know, so the conclusion is Sn, which states that 133 divides we had there 11 to the n plus 2 plus 12 to the 2n plus 1 for all n, integer, positive integer n, or natural number n. Questions about this? Do you understand, you know, this technique? Like I said, it's very simple, at least in principle. It's really simple. Okay, let's do another example. I think it's example 4, or I lost count. Not like we did too many so far, but probably will do. Let's prove something like this. Let's prove by using mathematical induction, the technique of mathematical induction, prove that this sum, let's say from k equals 0 to n of k times k factorial, looks pretty interesting, is in fact n plus 1 factorial minus 1. Well, before I use mathematical induction, you may say, how the heck did you get, this formula? We can prove this formula directly. So let me give you two different proofs. So let's say first solution, solution 1. Actually, which gives, you know, the formula. It's a very, let's say, well, it's an ingenious way to decompose this sum. Okay, so in fact, so it's based on this kind of decomposition, kind of a telescopic decomposition. So you can say here, look, you have k times k factorial. You can say something like this. K, you can write this as k plus 1 minus 1 times k factorial. I haven't changed anything in this term. Okay? Okay, but then look what I can do. So this is the sum from k equals 0 to n. All right. Now, if I multiply k plus 1 times k factorial, what do I get? Let me just write it like this. And then I have 1 times k factorial is minus k factorial. Okay, so what do I get here? Obviously, I'm moving in a really, you know, slow motion with everything, so everybody can follow what I'm writing. If you don't, let me know. Okay, so what do I have here? You know, for the first term, I have k plus 1 times k factorial is k plus 1 factorial. And then I have minus k factorial. Well, this is beautiful because, you know, look what we have. We have this kind of telescopic sum which collapses actually in the sense that many terms cancel out. So I have, for k equals 0, I get here 1 factorial minus 0 factorial. By the way, what's 0 factorial? Do you remember what 0 factorial is?
It's 1.
Okay, very good. Now here you have, for k equals 1, you have 2 factorial minus 1 factorial. Then the next term in that sum is 3 factorial minus 2 factorial. And keep going like that, right? The last one will be, maybe I should write a few more, the last two. So the last two will be, okay, so I have here, when k is n minus 1, you have n factorial minus n minus 1 factorial. And the last term, the absolute last term, is n plus 1 factorial minus n factorial. Now, okay, so look what we have. So we have, this is 1 factorial minus 0 factorial plus 2 factorial minus 1 factorial plus 3 factorial minus 2 factorial, and so on, right? Plus n factorial. So I expand, I mean, I get rid of all these brackets, and I have this nice sum, which admits lots of cancellations. We'll see that in a moment. Okay, so look at the cancellation. Lots, I mean, only 2 terms survive. So here you have 1 factorial with negative 1 factorial, 2 factorial with negative 2 factorial, 3 factorial with the term which appears here, n factorial with something, which appeared exactly here, n minus 1 factorial with something which was before. All in all, what survives are these 2 terms, n plus 1 factorial minus 0 factorial, this one and this one, these 2. 0 factorial, we said it's 1. So that's the direct proof of the formula. Now let's prove it by mathematical induction. Mathematical induction is a very rigorous and solid proof, provides a very solid proof. So the second solution. So let's assume that somebody, handed us, this expression. So somebody told us, well, the sum from k equals 0 to n of k times k factorial is n plus 1 factorial minus 1. Prove it. Okay, so we want to prove this. Well, again, by using mathematical induction. The first step, so step 1, the basis step. Well, so the basis step for n equals 1, right? So for S1 means that the sum from k equals 0 to 1. Maybe I can change, this notation, but that's fine. Okay, so maybe I should, change. Probably I should change it because it could become, confusing later on. So I say here, there is nothing if I change the index, the summation index. I call it I. So let's say from I equals 0 of I times I factorial, right? Well, what's this? This is for I equals 0, this is 0. The first term is 0. For I equals 1, well, I have 1 multiplied by 1 factorial, which is just 1. And obviously this equals 1 plus 1 because n equals 1 right now, right? 1 plus 1 factorial, which is 2 minus 1. This is correct. Now, let's assume that S sub k, which is this statement, that the sum from I equals 0 to the k of I times I factorial equals k plus 1 factorial minus 1 is true. And what we want to prove, so this is what we want to prove, that sk plus 1 is true. So this is what we want. S sub k plus 1, which says that the sum from I equals 0 to the k plus 1 of I times I factorial equals k plus 1 is k plus 2 factorial minus 1 is true. So this is what we want to prove. Okay? How do we prove it? I mean, how do we have this? Well, just notice that the sum from I equals 0 to k plus 1, right, of I times I factorial is just the sum from I equals 0, all right, to k, just k, of I times I factorial plus the last term, because this the first term on the left hand side contains k plus 1 term starting I equals 0 to k, and then you have one more, right, corresponding to I equals k plus 1, and that means k plus 1 here times k plus 1 factorial. This is the last one in this sum. Okay, now we know from our assumption that S sub k is true, meaning that this sum, which you see here, is just k plus 1 factorial, right, minus 1. And then I have plus the last term, k plus 1 times k plus 1 factorial. Factorial here, just a second. This tablet doesn't always listen to me. Again. Okay, now let's do some little algebra. Let's play with algebra here. Okay, so I can factor out k plus 1 factorial, obviously, right? So I can factor out k plus 1 factorial. So I have k plus 1 factorial because k plus 1 factorial is contained in both terms on the right-hand side in this of the above equation. So this is k plus 1 factorial, and what's left here is just 1, okay, plus k plus 1. And then we should not forget about negative 1, about this term. All right, very straightforward and really easy example. What we have here, this is k plus 2 minus 1. And fortunately, we observe that k plus 1 factorial multiplied by k plus 2 factorial is just k plus 2. I mean, k plus 1 factorial multiplied by k plus 2 is k plus 2 factorial. Here, minus 1. Well, but this is exactly S sub k plus 1, this statement. So that means, this is also true. And from these two steps, according to the mathematical induction technique, the statement is true. So conclusion, Sn, which in our notation meant the sum from k equals 0. K doesn't matter. This is a summation index of k multiplied by k factorial equals n plus 1 factorial minus 1. True for all n. True for all natural number n. Questions about this? Let's see some other kinds of exercises. Let me prove something, let's prove Bernoulli's inequality. So this is example number 5. You have many more examples in the textbook or the material you use. Like I said, there is an infinite supply of such problems in many areas, not necessarily in just in let's say identities or divisibilities. There are other important applications in real life, for real life examples and problems. Okay, this one is a very well-known inequality, the so-called Bernoulli. I don't know which one, James or Jacob Bernoulli, because there were 5 Bernoullis spanned over 200 years. So this was a very, let's say, well-known family of mathematicians. Bernoulli's inequality. It can be stated very easily. So it says that 1 plus x to the n is greater than or equal 1 plus nx. If x is greater than -1, so for x greater than -1, and n can be any natural number, including 0. But for 0, you don't have much because 1 plus x to the 0 is 1, and on the right hand side you have 1 again. So in fact, this inequality is an equality for n equals 0. So let's assume that n is a positive integer greater than or equal to 1. Okay, so we assume that n belongs to the set of all natural numbers, and without, let's say, 0. Some people consider 0 a natural number as well. Okay, how do we prove this? How do we prove this inequality? By using mathematical induction. Of course, you can prove this by using other methods, like binomial expansion, Newton's binomial, or you can even use Taylor's polynomials expansion, which is kind of the same as very similar to Newton's binomial expansion. But let's use mathematical induction. So let's not bother with a direct proof, in the sense that we don't want to expand the left-hand side of that inequality. We just want to use mathematical induction. Okay, so the first step is very easy. So S1, it says that 1 plus x to the 1 greater than or equal 1 plus 1 times x. Well, this is absolutely true, right? For all x greater than -1, because 1 plus x obviously is greater than or equal 1 plus x. It's like saying that 0 is greater than or equal 0. Absolutely true, right? It wasn't true if it was a strict inequality, but this is, it's not a strict inequality. So that was the basic step. The induction step, we assume Sk true, and we want to prove that Sk plus 1 is true. So that's the question, right? That's what we want to prove. Okay, so how do we prove this? So we know that Sk, which we assume true, is that it says that 1 plus x to the k is greater than or equal 1 plus k times x. This is what we have, Now, so we know that this is true. We multiply this inequality by 1 plus x. The direction of the inequality doesn't change, because for x greater than -1, and that's why we need x greater than -1, this quantity, that quantity there, is positive. So you don't change the direction of the inequality if you multiply by 1 plus x. Okay, so then what do we get? We get 1 plus x to the k plus 1. Okay, here this is greater than or equal 1 plus x times 1 plus kx. All right. So let's see what we get from here. So this one equals what? We can FOIL this product, and we have 1 plus x plus kx plus kx squared. Very nice. Now, if we rearrange, the terms, so this is what? This equals x plus k times x is just k plus 1 times x. And here is plus 1 plus kx squared, which is obviously greater than or equal 1. I'm going to, interchange these two terms, switch them, plus switch the order, right? Change the order. Plus 1 times x, and that's it. This term is always non-negative, so this is greater than or equal to 0. I just ignore it, okay? I ignore this term, so I bound this expression from below. This is true, right? But this is exactly saying that xk plus 1 is true. And we are done with the second step of the induction. And by that, we conclude. So the conclusion is that S sub n is true.
Professor, you said kx squared goes to 0.
Yeah, I mean, this is always, k times x squared is always non-negative, right?
Mm-hmm.
So you can discard it. I mean, you can bound this quantity from below by what's left. K plus 1, x plus 1, right? Which I wrote here.
Mm-hmm.
I mean, just, so you bound this by from below by this one, which is true. But this is all that we need. So, like I said, Sn is true, so meaning that Bernoulli's inequality is true for all n. N greater than or equal to 1, positive integer. Okay, let me give you one more such example, and then I don't know if we'll have time. If not, we'll talk next time about the proof by strong induction, which is a version of the standard induction. Example, I think it's 6 maybe. Let's prove this. For all, let's prove that for all natural numbers n greater than or equal 1. So these are integers, right? Integer. The following inequality is true. Sine, the absolute value of sine of n times x is less than or equal n times the sine of x. Okay, so it's an interesting thing, right? Well, here is the proof by induction. The basis step is kind of trivial, right? So this is our statement, Sn, right? This inequality is our statement. S1, obviously, sine of 1 times x is less than or equal 1 times the absolute value of sine of x, right? Because in fact, you have equality here. So this is no problem. This is for all x. I mean, for all x. For all x in R, element of R. I mean, this should be true for all real numbers x. That's the basis step. Now, for the inductive step, we assume Sk true, meaning that we have this sign of k times x less than or equal k times the absolute value of sine of x. We assume that this is true for all x, true. And then our task, our goal, is to prove that, so this is what we want. Sk plus 1, which is sine of k plus 1 x is less than or equal k plus 1. By the way, these problems are not from the textbook. I remember them from when I was, I don't know, in college, in high school. I even forgot since when I know these kind of things. I'm getting older. Okay. All right. We want to prove this. How do we prove that? Well, remember this trigonometric identity, sine of a plus b. This is sine of a times cosine of b. This is a very important identity. Times cosine of a. It's a symmetric formula times sine of b. Meaning that for the left-hand side of Sk plus 1, we have the absolute value of sine. Okay, sorry about that. I shouldn't have erased everything. So here, sine of k plus 1 x, I can write it as kx plus x, right? This is sine of k plus 1 x. And this equals, according to the above formula, to sine of kx times cosine of x plus cosine of kx multiplied by sine of x. And now the triangle inequality says the following, that this is less than or equal, I can say here sine of kx. I can also use the properties of the absolute value function, so I can write it like this, the first term. So I combine the triangle inequality with the property of the absolute value function, that the absolute value of a product is the product of the absolute values, okay? Makes sense, right? Okay, but this is less than or equal what? I'm going to bound from above these, terms. So I know that this one is less than or equal 1, right? It's the absolute value of cosine of x. So I can see here just sine of kx multiplied by something that is less than 1. Of course, if I bound it from above with 1, I increase this quantity. And then here, I can say that this is less than or equal 1 again. So I can bound it from above. So this is just, let me see, do I need sine? Okay, plus, okay, probably I don't want to bound this one, in fact. I have to keep the eyes on the price, right? So I'm going to bound the other one. All right, just a second. Okay, I'm going to bound this term, this one here. Obviously, this is less than or equal 1. It's cosine of something is less than or equal 1. So I can say here sine of x. Okay, now I know that this one is less than or equal from the fact we assume Sk true, right? So because Sk is true, so from Sk, I know that the first term, this one, is less than or equal k times sine of x plus Okay, so obviously I can factor out sine of x, and I get here k plus 1 times sine, the absolute value of sine of x. But this is exactly what I wanted to prove, because this is exactly s sub k plus 1. So this is true. Right, so this is what I proved. And from the mathematical induction, the conclusion is that S sub n true for all n. Okay. All right, I'm gonna stop here. So if you have any questions or anything, let me know, because I have another class immediately after, and see if you understand what we said today. Next time, I'm gonna talk about the strong induction. It's just an enhanced version of the standard induction technique. Okay. The attendance is taken automatically by Zoom, so I don't worry too much about that. And I'm gonna send the video to Norma, and she'll post it on Brightspace, so you can see it again if you want to. And that's pretty much it for today. Okay. Have a nice evening, and I'll see you in my classes or other classes, who knows. Okay.
Oh, I have a question. It's not related to this class, but it's like something else.
Okay.
So for Math 378, which is next semester, is that one line or person?
I have no idea. I mean,
Mhm.
we're still working on that, the schedule, and the things are very fluid. I really don't know.